So what we're going to do now is we're going to consider the case of a reflectionless potential. So essentially we've got rid of this. Remember there was a term here which had a reflection. So we're going to assume that. So basically we're assuming that the R is equal to 0. There's no reflection. So in that case here the F becomes rather simple. It looks like this. And we're going to substitute that into this integral equation. And what happens when we do that is we end up with, let's just do this, k of x comma y and t plus our function, so which is the sum of cn t squared e to the minus kn x plus y plus the integral from x to infinity of k of x comma z comma t e to the power of sum of e to the power of cn of t squared e to the power of minus k n y plus z dz. So the thing to do is to observe that everywhere there's there's a sum which we can pull out of e to the minus k and y that appears. There's an e to the minus k and y here. There's a sum of e to the minus k and y here. So it must follow that k, just make sure I add it in, whoops, add in the equals 0 here. Okay, so all of the side here is the sum of something times e to the minus k and y. So k of x comma y comma t must be the sum of something times e to the minus k n y. And the something, whatever this something is going to depend only on x and t. Okay, we add a minus in here just for convention. And this is the sum from n equals 1 to n, or whatever the number here is. I haven't written the sum in explicitly, but so what's going to happen is there's a linear equation, a linear integral equation. This is going to become a matrix equation when we substitute this in. So we substitute this into this equation. So we're going to get the sum here, and then we can do. We're going to eliminate the k and y's, and we can integrate this term here explicitly. So there's quite a bit of work to just jump down here. But we're going to, when we substitute this in. Alright, so what the heck to do here? The easiest thing to do, I think, is just to start writing at the top here. Just rub this out, and then we'll just take our equation. Whoops, don't do that. Just give it a rubbing, and then take our equation from be careful, and then substitute in here. So what have we got? We write kn is equal to this term here, so we're going to get minus, I'll change colour here, get something more radical, blue, minus the sum. Okay, I'm not going to write the sum out, I'm just going to trying to keep it a little bit simple here, e to the minus k and y plus, okay, and we're going to write this as m, so we don't muddle the sums up. So we've got the sum over n of cn squared e to the minus kn x plus y plus the integral from x to infinity of sum over m of bn e to the minus kn y sum over n of cn e to the minus kn y plus z dz equals 0. Okay, got to be slightly careful about all these numberings here. So these, inside the bracket here, these should be n's. Okay, because they're the same as the ones on the, from matching, they have to match these ones. and these sums here are the n's. All right, so now I'm going to rub this bottom bit out. Then we can go and integrate here. So we get minus this doesn't change, bn e to the minus kny plus sum over n cn squared e to the minus knx plus y. And then we integrate this, and the only thing we can get to integrate with respect to z, so we're going to get cn e to the minus kn y plus z, and then we're going to divide by kn, and then we're going to add in, we either put an x in, and we've got infinity, and we get 0, and we've got x, and we're going to get some value. All right, and I can see I've just done something silly, and that this should be a z here. That's an error. All right, when I despised it, that should be z. So what I'm going to end up with is, I'm going to end up with the sum with the sum over m, the sum over n, and with a minus sign here, I'm going to get cn, I've lost the cn squared here as well, cn squared over km plus kn times bm times e to the minus kmx e to the minus km y plus x equals 0. And this is a linear equation for Vn essentially. Every other term's known. We can eliminate the k and y's. They appear everywhere. And we can reduce the sum, instead of looking at the sum over n, we can just take each individual k. So we end up with Vn. So choose n and eliminate e to the minus k and y. We get Vn plus cn squared e to the minus knx plus the sum, minus I should say, minus the sum over m of cn squared over km plus kn times bm e to the minus 2 kmx equals 0. Sorry, km plus kn, whoops. Km plus knx equals 0. So that is that's just a linear equation for Vn. Each of these are constants here, and of course Vn depends on x, so this is how the x dependence comes into Vn. So we can write this as I'm not going to write it down, it's in the notes, but this is a matrix equation for Vn. So this sum over m here, let's get this correct. This is Vm. This is some matrix multiplied by the vector. This is a matrix multiplication here, effectively. All right. So we can, by matrix inversion, we can solve for Vn. So we solve for Vn, and then that leads us to K, which leads us to U. Okay, I'm going to leave it there. The notes are a little bit more detailed about it. But we're going to do, finally, we're going to do the single soliton example and actually go right through this calculation, but only in the case when there's a single one, so there's no sum here. So this equation just reduces to a single equation.